in this example, we're going to use the chain rule, but we're also going to be using the quotient rule at the same time. So the algebra is going to get a little messy, but we're just going to take it nice and slow, and things should be all right. So what I'm going to do here is I am going to use the general power rule, which again is for you in the upper right hand corner. And this time I'm not going to make the f prime, g prime chart, but I'm going to go nice and slow. So we're ready to find the derivative, which is going to be y prime is equal to, bring the exponent down in front, which is 2, rewrite the expression 3x minus 1 over x squared plus 3, drop the exponent by 1 to a 1, then multiply by the derivative of the inside. Well, this is the inside function, and it's a quotient, so we're going to have to multiply by the result of having done the quotient rule, which is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So this is looking pretty gross, but this is how it is. So we're going to clean up the upper right. Oh, that should be a y prime equals 2 over 1 3x minus 1 over x squared plus 3. Now what we have here is the denominator of x squared plus 3 squared. And now I've just got to clean up this upper right a little bit. So we have 3x squared plus 9. And then we have minus 6x squared plus 2x. And we're almost there, almost there. Y prime 2 over 1. I do that because I really want to keep track of who's in the numerator and who's in the denominator. And sometimes that 2 can drop down, but by putting that 1 there, you know where it belongs. Okay, so here we go. X squared plus 3 squared. And this is going to end up being negative 3x squared plus 2x plus 9. And then you look at this and you say, okay, x squared plus 3 happens once here and twice there, so that's really 3 times. So I'm going to do one final expression of the derivative, and that's going to be 2 times 3x minus 1 times negative 3x squared plus 2x plus 9 all over x squared plus, come on pen, don't fail me now, cubed. Okay, so very, very messy algebraically, but if you keep your cool, you do it nice and slow, one step at a time, you should be okay. And the other benefit of that is that if you do make a mistake, you can kind of look back and, you know, if it's neat and organized, maybe you could more easily detect where that error occurred. So this one was a chain rule with a quotient rule inside. The next two problems deal with the derivative of trig functions and how the chain rule is used in figuring those out. So it's actually pretty much the same as what we've been doing. You're taking the derivative of an outer function and then multiplying by the derivative of the inner function. So the derivative of sine is cosine, so what we're going to write is y prime is equal to cosine 2x, but then we've got to multiply it by the derivative of the inside or the inner function, which is 2. So when all is said and done, and I'm running out of room so I'm going to put it up here, we get y prime is equal to 2 cosine 2x. Okay. For 11b, the derivative of cosine is negative sine, So y prime is going to equal negative sine x minus 1, and then the derivative of x minus 1 is just 1. So finally, y prime is equal to negative sine x minus 1. Okay, and finally, the derivative of tangent is secant squared. So the derivative of tan 3x will be secant squared 3x times the derivative of the inner function, which is 3. I'll just rearrange that a little bit. So we get 3 secant squared 3x. Okay. Now, these are more trig derivative problems, but now that it's the question of where's the parentheses and how's that going to affect the answer and figuring it out. So this first one doesn't have any parentheses at all. So sometimes when that happens, you know, the cosine of pi, for example, you can put the pi in parentheses or you don't have to. So this one doesn't have parentheses. I'm actually going to put them in. So my argument is 3x squared. The derivative of cosine is negative sine. So y prime is equal to negative sine of the argument, but then times the derivative of the argument, which would be 6x. So when all is said and done, we get negative 6x sine 3x squared. Now, for this problem in 12b, we've got cosine of 3 in parentheses and x squared not in parentheses. Well, cosine of 3 is just a constant, so this problem could just as easily be y equals 4x squared. And if you saw that, the derivative would be 2 times the 4 that's already there, and then x. So if we kind of keep this in mind, this wasn't the actual problem, but it's sort of just like an analogous problem. Let's do it. So again, y prime is going to equal 2 times cosine 3, and then we drop the power by 1 to a 1, and then we just rearrange it so it looks nicer. We end up getting 2x cosine 3. Okay. Now this one, what I would probably do here is I'd rewrite first by just squaring the argument, because the only thing that's being squared here is the argument itself. So y equals the cosine of, and the argument now becomes 9x squared. So if you write it like this, now when we find the derivative, it's not going to be so bad. The derivative of cosine is negative sine, so it's going to be negative sine of the argument times the derivative of the argument, and then rewritten so it looks nice. So that's going to be negative 18 sine of 9x squared. Okay, now for D, what I think I'm going to do first is I'm just going to rewrite this in the following way. This is the same as cosine of x squared. So here I'm going to use that general power rule when I find the derivative. So the derivative is going to be 2 times the expression, which in this case is cosine x. I reduce the power by 1 to a 1, and then I multiply by the derivative of the inside, which is negative sine x. And then I clean that up, and I end up getting negative 2 cosine x sine x. So these problems aren't really that bad, but it's absolutely worth mentioning the use of parentheses and how shifting them just a little bit can really change everything. And if you just gloss over it too quickly, you might you might make a mistake. So what I think I'm going to do with this one is rewrite it as cosine of x all to the 1/2 power. When you do that, the problem and the one above it are pretty much the same thing. So we're going to say 1/2. We're going to write the expression cosine of x. We're going to reduce the power by 1 to negative 1/2. We're going to multiply by the derivative of the inside, which is negative sine x. And then we're going to clean it up, and hopefully we're going to find somewhere to do that. Let's see if I can write small with this horrible pen. We have on top negative sine x. And on the bottom there's a 2. And there's the square root of cosine x. All right, that was fairly successful. So in summary, taking the derivative of trig functions when there's chain rule is not too much different from what we had been doing in the past, but again, it does require practice, and there's this heightened sensitivity to the use of parentheses and how that's going to play out. The grand finale. We're going to do one last chain rule question that involves trig, but there's going to be a special bonus for you. Let's take a look. Y equals sine of 4t cubed. The first thing is I don't like the way that this is written. I think it'll be confusing, so I'm going to write it like this. Y equals sine of 4. Oh, that's a crazy looking 4. We're going to stick with it though. Sine of 4t cubed. Okay. Now that I've written this way, I'm going to use the general power rule. And I'm going to take the derivative. So the 3 leaps down in front. The expression in the brackets stay the same. Sine of 4t. I reduce the power by 1, and now I multiply by the derivative of the inside. The derivative of sine is cosine. But now I've got to chain it again. I've got to take the derivative of the new inside, which is 4t, and its derivative is 4. Crazy, right? So when all is said and done, I've got 12 cosine 4t times sine squared 4t. Double chain. Amazing.